Right. I will speak about cooperation networks, and really I will speak about cooperation. So the question I'll try to address is, why is there a network at all? Why aren't there just collections of nodes that have nothing to do with each other? So my starting point is such a collection of nodes. You have a bunch of nodes, but that's not a network. To have a network, you need to add some edges to those nodes. Why might you do that, or what might those edges actually mean? And we had, I think yesterday on slide 2 in Damon's talk, the word cooperation came up in the context of Duncan's paper from 1999, where he pointed out that, at least under certain circumstances, the local clustering makes it easier for, as he put it, cooperation to spread in a network. So a lot of this network structure, a lot of just structures in general that we observe in the world have something to do with cooperation. I'll break this down into a very simple, but I think relatively general setup. So I'll start with nodes. I characterize the nodes in a certain way, and then their character will lead to cooperation and those nodes linking up in a natural way. So I assume that nodes are something alive. And if you look up what something alive means, you can go to Harold Morowitz's book, for example, and see how he defines that. And he says that living systems self-replicate. That is, they give rise to organisms like themselves. So life can be defined as the thing that generates more of itself. And if you want to represent that mathematically, and you want a very simple model, that is exponential growth. So it's multiplicative growth. It's something that is generating more of itself. And in general, it does that in some noisy way. So this is sort of the model that I have for the dynamics of the individual nodes. If you did nothing to the nodes, they would just grow in a noisy, multiplicative way, as all things that live do, unless they hit carrying capacities and things like that. The edges between these nodes will be flows. So I'm thinking of resources. That these nodes are accumulating in a multiplicative way resources, and when they form a link, they share those resources with nodes that they have connected to, and these are mutual. This is mutual sharing, and in the first instance, I will just talk about what happens when both nodes put everything they've got on the table and split that evenly. So this is sort of total cooperation. You pick someone who's your friend and you just say, whatever is yours is mine, and we're in this together. Now, this kind of sharing, or this sort of cooperation, is not well understood. There's a problem with it. If you look at the expectation value of the resources that any one such entity accumulates, it's not affected by pooling and sharing, and nothing happens. And the reason for that is that I consider these resources to be conserved quantities. So this could be calories, or it could be money, or it could be something like that, some physical thing that you can share. But when you share it, it doesn't suddenly become more just because I shared it. It's literally something you put on the table, you split. Now, if we have this kind of setup, it doesn't affect your expectation value. And what's worse is that the richer entity, if you imagine two of these entities, and one is a big blob and one is a small blob, and they put what they've got on the table, the richer entity loses in that instance when the cooperation happens. So why should the richer entity, whoever that is, enter into such an agreement? Or why pool? Now, there is a standard answer. There are various answers, but there's one good answer, and that is new function. So you can imagine that you have a bunch of entities, and when they are separated, they can only do whatever they can do by themselves with the functions that they themselves can carry out. But when they link up, they may be able to create new functions. They may be able to do new things. Now, the problem with that standard answer is what is function. This is very difficult to define, and I won't really get into that. The real problem is for very small or simple or early networks that don't have any new function. So imagine a bunch of single-celled organisms, well, not organisms, single-celled life forms sitting around, and now imagine two of them join up. There isn't really anything that they can do because they are now a pair that they couldn't be doing before. It's even worse for this specific transition from single cell to sort of a cell that's joined up, because cells collect nutrients through their membranes, and when they join up, they lose some of the membrane to the outside world, so it actually becomes harder for them to collect nutrients. So there are certain barriers to be overcome. So there must be something else going on other than building new function. And the key insight that I will use in my talk is that growth is not an ergodic process. And we've actually made a hidden, unwarranted assumption when we made this first argument that expectation values of resources are unaffected by pooling. The expectation values are actually not the interesting quantity. And this is because the growth is not ergodic. So it's true that nothing is gained in expectation from this type of cooperation, but over time you do gain. So the notion of ergodicity is about comparing what happens in a probabilistic ensemble to what happens over time when a process unfolds, when a single instance of a process unfolds over time. And if something is ergodic, then those two perspectives on the problem, the perspective of viewing it as something that you can average in an ensemble or something that you can average over time, will give you the same answers. But if the process is not ergodic, then that is not true, and we have to be very careful in the mathematical objects that we use and how we interpret them. Okay, so to demonstrate what all of this means, I'll give you my favorite game that some of you, I'm sure, have seen before. It's very simple, but it illustrates the key points, so I always talk about this. It's about tossing a coin, and you toss this coin, and if it comes up heads, you win 50% of your biomass, whatever it is. If it comes up tails, you lose 40% of your resources. So over time, you will have some kind of a process that will be generated by this. Let's say you start, so in this case, let's call the resources money. You start with $100. You toss the coin, it comes up tails. You lose 40%, so you go down to $60. You toss the coin again, you lose 40%. You toss it again, you win 50%. You lose 40%, you win 50%. So you get some random trajectory out of this simple game. You can play this for a little while. In this case, I played for an hour, so 60 minutes. I'm tossing the coin 60 times, and it generates a trajectory for me that just looks like noise to me, nothing very interesting. Because this just looks like noise, we invented probability theory at some point, namely in 1654. This is a famous exchange of letters between Fermat and Pascal, where they tried to figure out what to do with such a system. And they said, well, maybe we should just imagine everything that could possibly happen in such a process, and then just take the average over that. And we'll call this average the expectation value. Now, one way of doing this is a Monte Carlo simulation, in which you just run the process over and over and over again, and you generate many, many of these trajectories, lots of them, and eventually you average over them. So now I've generated 20 trajectories. I take the average at every moment in time, and I still get something that's a bit noisy, so instead I'll take 1,000 trajectories or 1,000,000 trajectories. And what you see as you increase the size of your ensemble is that the noise diminishes and eventually completely vanishes, and you get something deterministic. And indeed, the expectation value is a deterministic object that has no randomness in it. And what you also see is that your resources in this case, well, that the expectation value of your resources in this case grows exponentially over time. So these are logarithmic scales on the y-axis. So you see growth at about 5% per round in this game, and that's what you would expect because we used a fair coin, 50-50. With 50% chance, you win 50%. With 50% chance, you lose 40%. So you win more when you win than you lose when you lose. Therefore, the expectation value grows exponentially. So the conclusion then is that this type of game is worth playing on average. When you offer this type of game to people, they won't play. This is an empirical observation. The question then becomes why? Why would they not play? I could ask you if you would want to play this game. I won't ask you if you want to play this game. And there are various solutions why people won't play. Most of them are based in some kind of psychological insight or psychological model of people, sometimes called irrationality, because it's clearly a beneficial game from the expectation value perspective. And utility theory is the big story here. So this was what was invented in economics to solve this sort of a puzzle. But there's an alternative perspective on the problem. You can say, well, the game is worth playing on average, but what do we mean by average? What we've seen is that this game is worth playing if we can average over essentially parallel universes, over many different realizations of how this might have played out. But in the 1870s, when probability theory entered physics, Boltzmann started asking the question what these expectation values actually mean. And specifically, he started asking, are they identical to averages taken over time? So we should just try that out. Take this game and play it for a long time, and then average, and see if there's a difference. Okay, so this is the first slide, the first trajectory that we had of this game. Again, 60 minutes, and now what I'll do is I'll just continue this trajectory. So I'll just play for longer, and as I play for longer, I'll have to zoom out of the picture because I have to put more data on it, and in this zooming out process, the noise will also disappear. So that's another way of getting rid of the noise. You just do something for a long time. So instead of an hour, I play for 24 hours now, play for a week, I play for a year, and after a year, you can see that the noise has completely disappeared from the problem. But what you also see is that this gives you a completely different picture of the quality of this game. So while it is true that you win in expectation, it is also true that you lose over time. This may be puzzling. I found it very puzzling when I first saw this. But that's good. It's a good kind of being puzzled because it's very helpful. Now this is really the essence or the reflection of this process being non-ergodic. Because it's not ergodic, there's really no reason to believe that what happens over time is what you see in the expectation value or in your ensemble average. So people won't play this game. Why? Because they would lose over time if they played this game. And we care about what happens over time. We care about the future. We don't care about the multiverse that we don't have access to. And here comes my shameless ad. This changes all of formal economics, which is built on expectation values. So this 1654 exchange of letters and then the subsequent utility theory solution from 1738 is the absolute foundation of economics. And this perspective, this little game, this little insight provides a completely different absolute foundation for economics. So my program is to redevelop all of economics. Start from zero and do the whole thing again, and you get a very, very different picture. Okay, but we're talking about networks, and I wanted to explain the link. Why a link? Now, the basic model was that the individual nodes just follow noisy exponential growth. In this case, oh dear, well, there's an error in this equation. There should really be an x in front of everything on the right-hand side. So in this case, you have noisy exponential growth. This would just be a random walk, and that would be quite boring. In any case, so the idea is that you have these individual blobs, and they don't interact. So the blue blobs just grow at every time step. Time is going to the right here. At every time step, they grow by some random factor. So there's time step 1, you're small, you grow, and the next time step you shrink a little bit, and then you grow a little bit. And the same thing happens for each, well, not the same thing, the same type of process happens to each node. So the red node would be a different node, and you see it over time, it's growing, and then shrinking. So they do this random multiplicative process. I can then plot the resources that these two entities would have over a little while. Here, 100 time units, and you see some, again, it's plotted on logarithmic y-axis, and you see some sort of a noisy, growing trajectory. Now, what was that about expectation value and so on? We can compute for this game, or for this process, we can compute the expectation value. That's very easy, and it gives you a growth rate for the expectation value. And we can then compare those noisy trajectories that we saw to the solution of the expectation value. And you see, well, actually you don't see very much. So I'd like you to keep this in mind, that you don't see very much. This is basically noisy. The expectation value is sitting there somewhere. If you're lucky, you could be a bit above it. If you're not so lucky, you can be a bit below it. But on average, that's what happens. Okay, now the other thing that you can compute is the time average growth rate for this for this misspelled equation that I showed you earlier. So this is just geometric Brownian motion, and you're computing the time average growth rate. I should point out why my name has anything to do with it, because it doesn't have much to do with it. The basic idea, or the basic argument, even the basic result that everything I do relies on is, well, it was probably first formulated in 1870 by a mathematician called William Allen Whitworth. He was a Cambridge mathematician, and he wrote a paper about gambling, and he used these types of arguments as an argument to advise people against gambling, because in this time average growth rate, you see that there's a correction term. So while the ensemble average growth rate just had this mu sitting there, the time average growth rate has a minus sigma squared by 2 up there. And that is a correction term that reduces your time average growth in response to noise. So the more fluctuations you have, the slower you grow. That's what this says. And Whitworth was someone who noticed that. He then became very frustrated. He tried to communicate this, and no one really understood it. So he quit mathematics and became a priest instead. In 1944, Ito developed stochastic calculus. This result comes straight out of stochastic calculus. Kelly has a famous paper from 1956 that finds the same thing. So the reason why I dare to put my name behind a result like that is that it seems that I was the first to connect this to the problem of ergodicity. So Kelly connects this to information theory. Ito does his stochastic calculus and didn't, well, it's rather abstract, so he just did not consider these problems at all. And Whitworth is a funny one, because he just approaches the problem in a very naive way, and he just calculates it. He says, well, what's the problem? So what I'm really doing is I'm attaching a label to it. I'm saying this is very, very fundamental. This is the problem of ergodicity that we began to understand in the late 19th century. And this explains why it isn't present in economics, which takes its mathematical basis from the 17th and 18th century. Okay, so what's this? Right, now I'm doing the same thing again. So I let these guys grow for a longer time, and I compare their trajectories to the trajectory growing at the expectation value growth rate and another trajectory growing at the time average growth rate. The green line, green straight line, I hope you can see that as the time average growth rate, and you can see that if you play this for long enough, they follow roughly that time average growth rate, whereas the expectation value just has nothing to do with what happens in real life. Now, what we saw from this little mathematical analysis from these two growth rates is that fluctuations reduce growth. If fluctuations reduce growth, sorry, I can't speak, then reducing fluctuations must increase growth. And that is the role of risk management. So risk management is not so much about changing how much things move up and down, but by changing how much things fluctuate, you change how fast they grow over time. Okay, here's the idea that now gets to explaining the link in a cooperation network. Cooperation reduces fluctuations. That's the cool thing. So you look at the higher order statistics. You look at the first order statistics. We said that it doesn't do anything to the expectation value. That's true, nothing happens there. But it does something to the fluctuations. And you know this. This is, you're pooling risk, you're building a portfolio, something like that. So you reduce fluctuations. Now, if cooperation reduces fluctuations, then that means cooperation increases growth. Just by itself. Just this simple process of pooling, sharing, reduces fluctuations, increases growth. That would mean that cooperators, so entities, these blobs that have figured out that it's good to cooperate, if they just make a deal and say, yes, I'm richer than you now, but I'll share with you anyway, who knows, maybe one day you'll be better off and you'll share with me. If they figure out that that's a good thing, they will outcompete the rest. They will outcompete anyone else because they grow faster over time. So what's this protocol that they would have to sign up to? It's a pool and share protocol. So this is basically one time step. So I have two entities here, two nodes, they're sitting there, I call them Y1 and Y2, they're now cooperators. The first step is they both grow. So they both experience some random factor by which they increase or decrease their size. Then they implement their cooperation protocol. And the cooperation protocol just means we both put everything we've got together, we put that on the table into one big blob, and then we split that big blob into two equally sized blobs. And they then belong to us again. So we've introduced something. We've just introduced this. Every time step now has we get together, share everything, and then the process starts over again. We grow individually or shrink, whatever happens. We pool, we share, we grow, we pool, we share, we grow, and so on. Now, okay, the curious thing in all of this is I said it reduces fluctuations, and it does. Without cooperation, now this is the correct equation. You have just geometric Brownian motion, and we worked out the time average growth rate for that. That was mu minus sigma squared by 2. This type of cooperation reduces the effective noise amplitude. So it sort of reduces the sigma. And it reduces it, and this will come as no surprise in this very simple setup, by a square root 2 factor. So the new equation now just has 1 over square root 2 sitting in the noise, and that reduces also the correction term that is affected by the noise. And therefore, it increases the time average growth rate. So again, we'll try this out. Now we have the same two entities that we had before, but so that's blue and red, and they follow the time average growth rate. And we've also plotted what would have happened to those two entities had they cooperated. So if they had cooperated, and I stress that they cooperate in a scheme that is conservative, there's a conservation law. They don't get anything just for cooperating. All they do is they reduce their fluctuations. But by doing that, over time, they grow at this higher growth rate. The pink line, again, is the expectation value growth rate. The green line is the time average for an individual entity. And the growth rate of the black line is somewhere in between, or it's exactly this mu minus sigma squared by 4. Okay, that's pretty much what I wanted to say. So the point is, this is how you generate structure. You start with disconnected blobs that live, and therefore follow multiplicative exponential growth. And then you let them invent. So you allow them to make a cooperation protocol if they want to. I have a list of sort of big thoughts. One is emergence. The cooperating whole in this case is very literally more than the sum of the cooperating parts.